this video, we're going to start talking about our parametric equations. Okay, so let's go back to the unit circle. With the unit circle, we know that this point B, okay, was no longer labeled in terms of x and y, but in terms of cosine and sine. So in other words, we found that the coordinates of this point were synonymous with the following. X was equal to the cosine of the angle theta. Y was equal to the sine of the angle theta, regardless of where this point was. First quadrant, second quadrant, third quadrant, fourth quadrant, regardless. Okay. At that point, you were actually being exposed to what we call parametric equations. And this is what we mean by parametric equations. So the position of something is dependent upon another variable. So the position of this point B, that is its x and y coordinates, are dependent upon a third variable, this angle theta. So that third variable is called the parameter, which makes these parametric equations. These two equations, okay, in which the x coordinate is dependent on one variable and the y coordinate is dependent on the same variable. Okay, so that's parametric equations. Now let's go and show you how we proceed with this on our calculator. Okay, so here we go. Okay, in our calculator we got to go to mode, and we got to choose from the mode the parametric. Okay, we also got to be in radian mode, and I'll come back in another video and guide you through everything we do on the calculator separately. Okay, so the mode was set to parametric and the angle to radian. Then I key in the y equals the cosine of the angle. Let's go back, and this is actually what I'm keying in. X equals the cosine of the angle. Now the parameter that's used on your keyboard is t, not theta. Really doesn't matter. It's just a variable. Okay. Largely that's because parametric equations usually the third variable is time. So the position of something is in respect to time. We'll look at that. Okay. And here the parameter represents the angle. So I keyed this in. Okay. And then I have to go and I have to watch my steps, my window settings. Okay, so what you can control now in the window settings are the parameter t, where you start, where you end, and with what frequency you want this to appear. Okay, so I'm saying start with the t minimum at 0. 2 pi is the t max, and the t step is this 0.13089, which is actually pi over 24. I'm resizing my window to be a 3x3 square, and I also have to zoom square on my window there. Okay, and so that should be the unit circle that we see. Okay, the same as what we saw with our basic unit circle problem. Now, how do we get from this to the equation of the unit circle? Okay, so this is these are the sets of parametric equations defining a circle. X is cosine theta, y is sine theta. And now if I choose to square both sides of both equations, that will give me x squared equals cosine squared, y squared equals sine squared. Now if I choose to add the x squares and the y squares, that would be the same as adding the cosine squares and the sine squares. So adding x squared and y squared is the same as adding cosine squared and y squared. And of course, here's our identity here: sine squared plus cosine squared equals 1. And there we come with the equation of the unit circle: x squared plus y squared equals 1. Okay, and in doing that, in moving from this sets of parametric equation to this equation in x and y, we've done what we call eliminating the parameter. eliminating the parameter. Now we've lost something in that sense too, and we'll take a look at that when we go to the calculator. Okay, make one slight alteration. Go back and key in the 3 cosine t and 3 sine t. All right, and see what happens. And of course, we can work it out here, eliminating the parameter down here. We'll show that this is a circle of radius 3. All right, and we'll show that this is the circle of radius 3. So eliminating the parameter, same as we did up here, we take it out of parametric mode and put it into a more functional mode. Even though this isn't legitimately a function, that should give you some glimpse of why we're going to use parametric equations, because we're going to start talking about things that in essence aren't functions as we know of, that is graphs that pass the vertical line test, and kind of limiting if we keep ourselves talking to that. Okay, now we're changing it up a little bit. We're going to say, well, what if I change the coefficients of the cosine and the sine? So I key in x equals 4 cosine theta and y equals 2 sine of theta, and we see, well, how would I eliminate the parameter on that? Well, I would choose to isolate the cosine and isolate the sine, as you see here. Then I'll choose to square both sides. Okay. So if I choose to square both sides and then add up the left side and the right side, this is what we're looking at. And of course, cosine squared plus sine squared once again is equal to 1. So this is what is going to be an ellipse. Okay. So we have generated an ellipse with that set of parametric equations. All right, and if preferred, we could actually eliminate the denominators here, multiplying by a common denominator 16, and we have x squared plus 4y squared equals 16, which, if you'll remember, I actually gave you things of that sort and ask you to graph by finding the intercepts of each. Well, to find the intercepts, if find the x-intercepts, you set y equal to 0, so you got x squared equals 16, so the intercepts on x are 4 and negative 4. Likewise, find the y-intercept, set x squared is 0, and you find the intercepts on y are 2 and negative 2. And so that's what we would find up here. Okay, we'd also agree that we'd also have a high degree of symmetry here, because if x is, since all x's are squared, is symmetric with respect to y, and since all y's are squared, it's symmetric in respect to x. So you actually came up with that graph some time ago, okay? Of course, here are the coordinates that we spoke of. Now let's talk about the graph of this ellipse and talk about it in a more general sense, okay? So an ellipse can be represented parametrically with sets of equations looking like this: x equals a cosine theta, y equals b sine of theta. All right, by dividing by a and dividing by b, then we could represent this in a more functional format. Okay, so dividing by a, dividing by b, and squaring both sides, we're going to end up with this as our equation. Graphically, what does that illustrate? Okay, well, again, if I want to find the x-intercepts, y is going to be equal to 0. That's going to make this whole thing 0. So the x-intercepts are going to be a and negative a, and the span DE is called the major axis. That major axis, then, as you should well imagine, is 2a, right? Okay. Likewise, the span from F to G is, okay, the span between the two y-intercepts, which is 2b, and that's going to be the minor axes. Okay. So we got the major axes and the minor axes, and of course, if they were equal, then this thing would be a circle. All right. And the major axes and minor axes are just whichever is longer. It's not necessarily coincident with the x-axis and the y-axis. It is that this if I switch these values here, then I would switch the major and minor axes and kind of have this elongated along the y-axis there, rather than the x-axis as it shows. Yeah, we'll talk a lot more about the ellipses in a moment. Okay, so we're gonna stop the video at this point and resume in the next video.